Okay, good afternoon, lads and ladies. Today, we are going to look more closely at the connection between the calculus operations, derivatives and antiderivatives, and the area problem. Specifically today, we are going to learn about the definite integral and the fundamental theorem of calculus. So we'll be going into detail on the things that I introduced to you at the end of last week. Last Friday's lecture, remember we gave kind of a nice primer of the fundamental theorem of calculus, part 1 and part 2. Today we're going to go through that more methodically. Before that, I want to take a quick look at your syllabus and just kind of remind you where we're going and what our timeline is like, because we're a little bit off from the timeline of the syllabus. First things, you may have noticed, we did talk about it a little bit, that the last day for a W was back on Halloween. It was the last day of this week, I believe. If, however, you've decided now that exam 2 is all done and graded, that you do not want to stay in the course, that there's no possibility for you to get out of this course what you need, then you should talk to me. Come to me during an office hour or send me an email and we can talk about it. I can withdraw people up to the end of the class, but if you go beyond the last day of class, I cannot withdraw you. And depending on certain financial aid things, if you're a dual enrolled student or a veteran or you're getting a scholarship from somewhere that is beyond my control, I might not be able to do that. So if you are thinking, oh shit, I should withdraw, but I can't anymore, come talk to me in office hours, or better, send me an email and we can sort it out. We'll see what our options are. We should be able to make something happen for you. The material that we're going to be covering this week is the material that was slotted for 11.2 through 11.6. We'll be talking about FTC1 and FTC2, definite integrals, which is a little bit of a 5.2 here, and maybe indefinite integrals this week. So yeah, here, sorry, let me show the screen here. So yeah, the last day for a W was the end of this week, week 10, which ended on 10/31. So if you would like a W, but you're concerned that you cannot get it now, come see me, or better yet, send me an email. The material we've been covering, of course, is areas and sums. We've talked a little bit about definite integrals. So this week, we're going to pick it up there, talking more about definite integrals and doing our formal work on fundamental theorem of calculus parts 1 and 2. Josh asks, are all grades in for exam 2? I'm going through and doing my grade cleanup right now. So I'm going through and grading all the study guides and also grading all of the exams that sent me work through non-conventional channels. So if your work wasn't uploaded to the regular place, if it wasn't sent to that assignment that says, exam 2, submit scans of your work here, then I'll be grading that today. That's what I'm working on right now. So most of the exam 2 grades are in. If you took the exam on the regular day and you submitted your work through the correct channel, then that was all graded and in, I think, by last Wednesday. But if you did not do that, if you sent your work somewhere else or you took a makeup test or something like that, then I'm grading those today. I see also here, wasn't able to make last week's lecture on Friday. Could we do a summation formula example like the homework that was due last Friday? Yeah, I can do one more example with those summation things. No, exam 2, Daniel, was 2 weeks ago. 2 Wednesdays ago, not today. Exam 3 is going to be like the last week of class. No, you don't have an exam today. Elisa, I will look back. Yeah, so I am going through and trying to clear out everything that hasn't been graded. So if you've handed in study guide 1, you handed in late or whatever, if you didn't get a grade, then I will be getting those in as well. Yeah. It may take a little time. I get things sent to me from people weeks late sometimes, and I found somebody's exam 2 work buried in the study guide 1. So shit like that is happening, right? I've got a lot of different places I need to look to try and make sure I'm giving everybody the credit that they deserve, even if they handed things in a weird time or weird place. So it's going to be a process. But I'll say this, if you notice that by the end of the week this week, if there's something that you handed in or did, but you don't have a grade for, please reach out to me. I'm doing my best to look in all the little corners and crevices where things can land, besides where they're supposed to land. And and make sure everybody gets grades for that. But if there's something that you think you handed in that you don't have a grade for by the end of this week, go ahead and start pestering me about it. But I should have pretty much all of that wrapped up today, unless there's something in an absolutely bizarre place. Okay, I think that's all the bookkeepy stuff, so let's get to the mathematics. This is MAC2311, section 004. It's a lecture. And today is the 16th of November. All right. Yes, Sophia, that's correct. So if you get a grade on the final that is higher than your lowest midterm grade, then the final exam grade will replace your lowest midterm grade. So suppose your exam 1 is a 50, you know, exams 2 and 3 are like 80s, and then the final exam is like a 75. We can run through this really quick. So final exam replacing lowest midterm. All right, here's a hypothetical. Maybe on exam 1, you get a 50%. Exam 2, maybe you get a 75%. Exam 3, maybe you get an 80%. And then on the final, maybe you get like a 76%. Then what will actually go into the grade book, the final could replace either exam 2 or exam 1 because the final is better than both of those, but it will only replace the lowest. So what will go into the grade book, I will update the grade book after the final, and your exam 1 would be a 76 because I would have replaced that. Exam 2 would stay the 75. Exam 3 would stay the 80. And the final would stay the final. Is this making sense? So the final replaces your lowest midterm if the final is better than that lowest midterm. You'll see me making these changes after I grade the final. I'll post an announcement letting you know that I've wrapped up the grade book and that everything should be in, and then I'll post a separate announcement letting you know when the grade book has been updated with the final exam replacement stuff. So you'll have a chance to look at your completed grade book before the final replacement, but with everything in, and then you'll have a chance to look at the grade book with everything in and the final exam replaced. So you should have a chance to kind of take a screenshot and look at both of those situations and make sure everything is as it should be. Okay. So today, I'm going to talk about the definite integral, this is section 5.2, and the fundamental theorems of calculus. Which is section 5.3. The section 5.2 is largely about notation, but there are also some rules that come along with that notation, and you need to remember all of that stuff. So let's get started. I'll just show you. Here's the symbol, right? This is called the definite integral of the function f of x from x equals a to x equals b. And there's a few ways to understand what this says. Intuitively, it's the area bounded by f of x and the x-axis on the interval a to b. And the only catch with this is that it's really the signed area. S-I-G-N-E-D. Sorry, this document camera's resolution seems to be dropping by the day. And it's also the limit as n goes to infinity of Rn, which is, remember, the limit as n goes to infinity of sigma, I should say I, from 1 to n, f of xi times delta x, where xi and delta x are the thing that we've been using. It's all well and good. There are problems, like in your homework from last week, where you need to be handed a Riemann sum like this and interpret it as an area. But for the most part, moving forwards, we will not fuck with Riemann sums, right? We're pretty much done with this. I will show you one example because I think somebody asked for a summation example, so I'll do one of those. But moving forwards, we're going to be thinking of it like this. So I want to talk about what we mean by this word signed, and just a little bit how you can interpret that. Before we get into those explicit things, though, I want to talk about the notation. So this piece right here, this is an elongated letter S, right, with the A and the B. But this big symbol right here is an elongated letter S, and it's called the integral symbol. So this part right here is read as the integral from A to B. So the middle thing here, the S, is called the integral symbol, and these numbers here, A and B, are the numbers A and B from your Riemann sum, from the area. It's the X values that you're looking at finding the area under. The dx at the end, this is called the differential term. Unfortunately, we really don't have the tools in Calc 1 to explain in detail what this is. It's called a one form. It's a differential form, which is a mapping from a vector space to the real numbers. But for your purposes, for our purposes, the dx tells you what you're integrating with respect to. Just like when you look at d over dx, that says differentiate this with respect to x, or d over dt says differentiate this with respect to t. Think of the dx for now as telling you what you're integrating with respect to. Tells you you're going to do this calculus operation with respect to this variable on this function. And f of x is called the integrand. The thing that's being integrated is called the integrand. Just like the thing under a radical is called the radicand, or the thing inside of a sum is called the summand, the thing inside the integral is called the integrand. you can think of dx as a very small delta x. So the integral, this thing in black, is the limit of the sum. So kind of the capital sigma here becomes this capital S. The f of xi's are like the f of x, and the delta x is like the dx. Dx can be thought of as an infinitesimally small delta x. So very small. By very small, I mean infinitesimally. And because this concept has been around for so long, more than one person has tried to make it rigorous, and that means there's more than one way to talk about it. The modern way to do it is to talk about dx as a one form, but back in the day, they used to call it an infinitesimal. Basically, f of x at any particular x value is the height of the function, and dx is sort of the width of that point. So what we're doing here is we're summing, we're adding up all of these little heights times these little widths to get the area. It's just that rather than having a finite but measurable little width like delta x, you have an infinitely small little width, dx. All right. That's the notation and terminology. But how do we really understand this shit? So make sure you remember these words, right? That's all I'm trying to do here is introduce the words. The S is an integral. The thing inside the integral is called the integrand. And what it does is it measures the signed area between bounded by f of x and the x-axis on the interval AB. So let's draw some pictures. Okay, I'll leave this here for just a second in case anybody is still writing. So every time I've drawn one of these general pictures in the past, the function in question has been positive. I've done that to avoid the sort of subtle discussion that we need to now have. So here's the x-axis. Here's some function. Okay, we'll say this is the graph y equals f of x. So the function being graphed here is f of x. Maybe little a is right here, and little b is right here. What I want to do is understand the integral from a to b of f of x dx, which remember is the signed area bounded by this curve and the x-axis from a to b. Well, that's definitely this area, and this area. This first area, let me call this A1. The second area, let me call this A2. And this third area, let me call this A3. Then the integral here is going to calculate the area A1 minus A2 plus A3. This guy is being measured as negative because it's below the x-axis or the horizontal axis. right? So the values of the function here are all negative, which means the contribution to your Riemann sum from any rectangle that comes from this piece would be negative because the f of xi's there would be negative. And the point of the integral is to measure the signed area. So this is what we mean by signed area. Stuff above the horizontal axis is measured as positive. Stuff beneath the horizontal axis is measured as negative. It would be very possible to define the integral so that it measured all the area as positive. But it turns out that this is a more useful construct. This has more applications to physics. And if you just want to get the area that's bounded, you don't want the signed area, then you would calculate A1, A2, and A3 separately, and then just change the sign of A2 to make it positive. So this is what we mean by signed area. Are there any questions about that concept? So if I told you that A1, this area here was 5, this area here is 8, and this area here is 7, then the integral would be 5 minus 8 plus 7, right? There are problems like that in your homework, so it's an important concept to digest. The next thing I want to talk about are some properties of the definite integral. So just like properties of logarithms are algebraic statements that the logarithm satisfies, properties of the definite integral are kind of the algebra of this symbol. One of them is that if you integrate from a to b some function, f of x dx, and you add that to the integral from b to c of that same function, that this is equal to the integral from a to c of that same function. So if you look at the area from a to b, and you add that to the area from b to c, that is the area from a to c. The picture that goes along with this, very intuitive. I'll draw it over here. And I'll draw it with f of x being positive. This is the integral from a to b of f of x dx. This is the integral from b to c of f of x dx. And all of it together is the integral from a to c of f of x dx. So if you integrate from a to b, that gives you this first area. If you integrate from b to c, that gives you this second area. So of course that's the same as the integral from a to c, which is all the blue area. This next property is not as obvious. Usually we think of a as the smaller number and b as the larger number. But if you flip those over, that just negates the integral. This has to do with what's called orientation. You can think of it as the delta x here would be negative, right? If a is the smaller number and b is the larger number, then when you take this minus this over n in your Riemann sum, delta x would be negative. So for example, if the integral from 0 to 5 of f of x was 2, then the integral from 5 to 0 of f of x would be negative 2. These are the two main properties that I need you guys to know. Let me see, I could include the other ones here, but I don't want to give you too much at once without examples. So maybe we will go more slowly. Let me see how the book chooses to do this. Integrand, definitions. Yeah, no. Okay, properties. Yeah, okay. We'll piece one more in there, and then we'll talk about these. All right. So I'm going to go ahead and add these on right now, and then we'll look at examples in a minute. Another important fact here is that if you integrate from a to a, f of x dx, you're asking for the area under the curve, f of x, from some number to that same number. This is always 0, because the width of that region is 0. So the area has to be 0. Continue here. The next one, this is a big deal. Integration is linear. And really this can be said in one line, but your book says it in two, so I'll say it in two. If you have an integral of a sum of two functions, and you should always write such things in these big parentheses like I'm doing here. Always put your integrand in these big parentheses if it is split up by addition or subtraction, sum or difference, then you can do each piece on its own. That's the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So the area under f plus g is the area under f plus the area under g. That's all. And then the integral from a to b of a constant times your function is equal to the constant times the integral from a to b of your function. Constant multiples pop out. This is for any constant c. Has to be a constant. Only constants pop out, but constants do pop out. 4 and 5 together, these have a special name. This is called linearity. This means that the integral is a linear operator. So sometimes you'll hear people refer to these two things together by saying the integral is a linear operator. It's especially important later on in higher math classes. There's one more thing that your book does include here, although I'm hesitant to include it. We'll go ahead. The integral from a to b of any constant function is just that constant times b minus a. And there's a picture here, of course. If your function is a constant function, then its graph is a horizontal line. So the area bounded here is a rectangle. Its height is just c. Times its width, which is b minus a. All right. So these are the fundamental properties of the definite integral operator. We can use these to solve lots of problems. For example, if the integral from 0 to 7 of f of x dx is equal to 12, and the integral from 5 to 7 of f of x dx is equal to 3, then what is the integral from 0 to 5 of f of x dx equal to? Who can help me out with this one?
For the first one, is that 0 to 7?
Yes. Yeah, this is 0 to 7. This is 5 to 7. And this is 0 to 5.
So 15.
I'm sorry?
15 is the
It's not going to be 15,
Is it
but I think
9?
we're on the right path. So the integral from 0 to 7 of f of x dx should be equal to the integral from 0 to 5 of f of x dx plus the integral from 5 to 7 of f of x dx, right? That's property 1 that it seems like you're thinking of. Now let's see which pieces here do we know and which pieces here do we not know. Do we know what this guy is?
12?
Yeah, this is 12. Do I know what this guy is?
No.
No, that's the thing I want. Okay, so let's leave that. Plus, do I know what this guy is?
3?
Yeah. So if I subtract 3 from both sides, 12 minus 3 is 9. I'll get 9 is equal to the integral from 0 to 5 of f of x dx. That's it. And if you're having a hard time with this, you could always try thinking of the picture. Sure, I don't know what the function f of x is, but I can draw like a generic looking function and say, okay, well, from 0 to 7, I know that this whole area is 12, and from 5 to 7, I know that this area here is 3. So if the whole area is 12, if the whole area is 12 and this little portion is 3, then this portion has to be 12 minus 3. Is that making sense? Okay, let's try one more. What if I gave you the graph of f of x and some areas? Do it like this, and let's say here is 5 and here is 1. I tell you that the area here is 2. The area here is 1. And the area here is 1/2. Can we say, what is the integral from 1 to 5 of f of x dx?
1.5.
Yeah, good. I take this, I subtract this, and then I add this. The integral from 1 to 5 f of x dx would be 2 minus 1 plus 1/2, which is 1 plus 1/2, or 3/2, so 1.5. Okay, let's try a couple more that play around with these properties. First, any questions on these two?
So you would only count the positive?
The area that's above the x-axis is counted as positive. The area that's below the x-axis is counted as negative. So even though this area is 1, when I measure it with the integral, it contributes a -1 because it's below the x-axis. So these two are both counted as positive, and this one is counted as negative because these two are above the x-axis and this one is below the x-axis. That making sense?
Yeah, thank you.
Cool. Okay. Marching right along. If f of x is graphed below, what is the value of the integral from 2 to 0 of f of x dx? This point right here is 1, 1. This point right here is 2, 1. How would we get started with this?
Can you find like the area of like drawing a square and a triangle out of the two pieces?
Good. Yeah, this is a rectangle and a triangle, right? Let's call this A1. We'll call this area A2. Then the integral from 0 to 2 of f of x dx, from 0 to 2, mind you, not from 2 to 0. The integral from 0 to 2 is A1 plus A2. What's the area A1?
1/2.
Good, it's 1/2 base times height. And the base and height here are both 1. So this is 1/2 times 1 times 1 plus, what's the area A2?
1.
Good, yeah, the base here, this is a rectangle. The width is 1, the height is 1. So this is just 1 times 1. So altogether, this is 1/2 plus 1 is 3/2. Therefore, what is the integral from 2 to 0 of f of x dx? Think about those properties. Which one of those 6 properties is useful here? Yeah, Josh has it. This is the negative of the integral from 0 to 2 of f of x dx, which is negative 3/2. Remember, the integral from b to a is the negative of the integral from a to b. If you flip the bounds, you pop out a negative. All right, while we're here, call this part A. Part B, what is the value of the integral from 0 to 1 of 7 f of x dx? Which property could I use here?
Property 5.
Right, yeah, constants popping
Pull out the
out.
constant.
Yeah, so this 7 is a constant multiple inside, so he can pop out. So that's 7 times the integral from 0 to 1 of f of x dx. Okay, what is the integral from 0 to 1 of f of x dx?
One half.
Good. This is 7 times this first area, A1. And that first area, A1, we calculated earlier as 1/2. So this is 7 times 1/2, or 7/2. Any questions on these two? All right, then I'm going to try one more here. What is the value of the integral from 1 to 2, 3f of x minus 5 dx? And again, you see I'm putting the whole integrand in parentheses here. Any ideas how we could get started with this? Think of that fourth property, the linearity, the first of the two linearity properties. Good. First, I need to split this up. This is the integral from 1 to 2 of 3f of x dx minus the integral from 1 to 2 of 5 dx. All right, I'm thinking here of this property. Now that first piece, this piece, I can pop out the 3. So this is 3 times the integral from 1 to 2 of f of x dx minus, what is the integral from 1 to 2 of the constant function 5?
5.
Good. This is 5 times 2 minus 1. In other words, 5 is a constant function, right? So you can think of that area as just being a rectangle, and 2 minus 1 is 1. So this is just going to be 5. What is the integral from 1 to 2 of f of x? This 3 will come along for the ride. What is this piece?
1.
Good. So this is 3 times 1 minus 5 times 1, or 3 minus 5 is negative 2. Cool shit, right? So plenty of your homework this week is going to be just this sort of thing. Playing around with these basic algebraic properties of the integral, thinking about things as areas. Let's see how we're doing for time. Okay, we're doing good. There are some other fun properties having to do with symmetries. I want to make sure that I don't lose you guys in the weeds here, though. So we've talked about those. Comparison properties. Yeah, we can talk about that, but I'm going to save that for the end. So I think this is a good time to talk about one of those summation problems. It was requested that we do an explicit problem working an integral as a sum. So let's do that. So let's write the integral of let's go from 0 to 2 of how about 2x plus 1 dx has a limit of a Riemann sum. And then evaluate that limit. Okay. We did one of these last week, but it doesn't hurt to look at another one. These are kind of tough problems, so it's okay to do this. And plus, now we get to think of it as this integral. We get to think of it in this context. So remember, the integral from 0 to 2 of f of x dx, this should be the limit as n goes to infinity of the sum I from 1 to n f of xi times delta x. So we need to compute delta x, we need to compute the xi's and then plug those into f. Then we'll try to simplify this sum a little bit, and then we'll take the limit. So delta x is always b minus a over n. What are a and b here? A is 0 and b is 2. So delta x here is just 2 over n. And the xi's are always a plus I delta x. A again is 0, so this is 0 plus I times 2 over n, I'll just leave it like that. No harm in leaving it like that. We'll call this I times 2 over n. So then this integral is a limit. N goes to infinity. Sigma I from 1 to n. F of this times this. And my function f of x here, my integrand, is 2x plus 1. So this is the limit as n goes to infinity, sigma I from 1 to n, f of I times 2 over n is 2 times I times 2 over n plus 1. And then delta x is just 2 over n. So this is the sum that we need to work with. First, I would bring the 2 over n out front. I can bring it all the way out of the series, all the way out of the capital sigma. And then I would clean up what's left inside. This is I times 4 over n plus 1. just multiplying the 2 and the I times 2 over n. So from here, I have lim n to infinity, 2 over n, and then I would split the sum up. This is sum I from 1 to n of I times 4 over n plus sum from 1 to n of 1. Sorry, I used a square bracket there, so I used a square bracket. So I'm splitting this sum up over these two things. The capital sigma follows the exact same algebra rule as the integral. If you don't remember these rules from pre-calculus, you can think of them as a consequence of the rule for integrals. Then there's one last thing we need to do before we can apply the summation formula I gave you guys. All right, this is lim n to infinity, 2 over n, bracket. This 4 over n can also come out of the first sum. So that's 4 over n, sum I from 1 to n of I, plus sum I from 1 to n of 1. Now you have to remember those summation formulae. The sum from 1 to n of 1, this is just 1 plus 1 plus 1 plus 1, n times. So this is equal to n, right? 1 plus 1 plus 1 plus 1 plus 1, n times is just 1 times n, it's n. And then there's the summation formula that I gave you, sum from I equals 1 to n of I itself. This is 1 plus 2 plus 3 out to n. This is n times n plus 1 over 2. So that first formula I can use here. That second formula I can use here. So I'll have lim n to infinity, 2 over n, bracket 4 over n times this, n times n plus 1 over 2, plus this, which is just n. And now we can do some algebra. This n and this n cancel, and I can distribute my 2 over n. So I get lim n to infinity. See, these ends have canceled. Here I'll have 4 times 2 times 4. I'll just write it all out. This is 2 times 4 times n plus 1 over n times 2, or 2 times n, plus 2 over n times n, which is just 2. So we distribute. And we get this. These 2's cancel, and you end up with lim n to infinity. I can distribute the 4 here if you want. That's 4n plus 4 over n plus 2. So the limit as n goes to infinity of 2 is just 2. What's the limit as n goes to infinity of 4n plus 4 over n?
4.
If we renormalize, dividing top and bottom by n, that's 4 plus 4 over n divided by 1 plus 2. And as n goes to infinity, the 4 over n goes to infinity, so you get 4 plus 0 over 1 plus 2, which is 4 plus 2, which is 6. So these Riemann sum problems where you have to express an integral as a limit of a Riemann sum, then evaluate the Riemann sum, then evaluate the limit, they're long problems. And they all require something like this at some stage, which make them quite tedious. Now, though, we could solve this much faster. So I'll give you a minute if you're writing any one of these steps down. Please go ahead and get them down. And I'll show you a couple other ways to evaluate this integral. Five more seconds. The 4 over n piece here, I divided top and bottom everywhere here by n. So 4n divided by n is 4. 4 divided by n is 4 over n. That's the piece you're asking about. And downstairs, n divided by n is just 1. So I took this expression and divided every single piece by n. That was an answer to Daniel's question in chat. Any other questions here before I show you a much nicer way to do this problem? It is important that you're able to do this, right? This would be, I get questions like this a lot, like, would you put something like this on a test? Yes, absolutely. And this is about the level of difficulty that I would put on a test for this problem. Like if I was gonna, on the exam, make you evaluate a limit of a Riemann sum explicitly, go through this whole thing, this is about the level of difficulty that I would go for. Nothing harder than this. But this is still quite hard. Now, if I wanted to get that area through other means, rather than as a Riemann sum, how else could I do it? Well, I could say that's the integral from 0 to 2 of 2x dx plus the integral from 0 to 2 of 1 dx, and then say, okay, that's 2 times the integral from 0 to 2 of x dx plus the integral from 0 to 2 of 1 dx, and then draw a few graphs. Here's the graph f of x equals x. So this area I can crunch. And here's the graph of 1, the constant function 1. So here's the area being measured by the second integral. This guy tells me that the integral from 0 to 2 of x dx, I can compute that area geometrically. It's 1/2 base times height. This is the point 2, 2, because it's the graph y equals x. That would be 1/2 2 times 2, which is just 2. And here, the integral from 0 to 2 of 1 dx is just 1 times 2. It's the height times the width. So my integral, 2x plus 1 dx, we said is 2 times the integral from 0 to 2 of x dx plus the integral from 0 to 2 of 1 dx is 2 times this thing, which is 2, plus this thing, which is 2. That's 4 plus 2, which is 6. And I would say that this is a damn sight easier than the Riemann sum. And there are still other ways to do this. In fact, I will be showing you an even higher brow attack. Because what if these curves weren't so nice? What if this wasn't a triangle, but something harder to work with? What if this wasn't a rectangle, something harder to work with? We do need still more skills, but this is a good start. Being able to see the integral as a Riemann sum, the limit of a Riemann sum, and also see it as an area that you can calculate geometrically. And it's no coincidence that both of those came out to 6, because they're measuring the same area. Okay. Yeah. There is another kind of property of the definite integral that we need to talk about before I can introduce the fundamental theorem of calculus. So I will probably save our formal FTC work for Wednesday. We'll think of today as just learning about the definite integral. There are some comparison properties. Of the definite integral. So one of the things that analysis is the subfield of mathematics that works primarily with calculus. One of the main things that analysts try to do is estimate integrals. Turns out that's kind of tricky, actually calculating them. So we have lots of tools for estimating integrals. Suppose f of x has absolute min little m and absolute max big M on the interval AB. Remember, any continuous function on a closed bounded interval always has an absolute min and an absolute max. That was one of our theorems from section 4.1. Let's draw a picture what this might look like. All right, so maybe here's A, and maybe here is B. So the absolute min occurred right here. So this y value would be little m. The absolute max occurred right here. So this y value would be big M. Then the actual area here, which I'll shade in blue, obeys an inequality. On the one hand, the function never got bigger than capital M. So the blue area has to be smaller than the area of the red rectangle. And pretend like this is hitting that point right there. Okay. The actual area, the blue area, has to be smaller than the area of the red rectangle. Why? Because it's contained inside of there. So now the actual area, the blue shaded area, this is the integral from a to b of f of x dx, right? The red rectangle area It's a rectangle. So its width times its height is its area. That's capital M times B minus A. And I'm going to draw one more rectangle. It's going to be a purple rectangle. The purple rectangle has area its width times its height. Well, its height is little m, and its width is also b minus a. Which of these three areas, blue, red, or purple, is largest? The question clear? Yeah, which rectangle has the largest area? It has to be the red one. Then the red is bigger than the blue or the purple. What about the blue and the purple though? Which one is bigger, blue or purple? The blue is bigger, yeah, because the purple fits entirely inside the blue. The purple has to be smaller than the blue. Because the blue fits entirely inside the red, the blue has to be smaller than the red. So we have an inequality. The purple has to be less than or equal to the blue, has to be less than or equal to the red. And this is by containment. They fit inside each other. So because the purple fits inside the blue is bigger than the purple. Because the blue fits inside the red's bigger than the blue. What this means is that little m times b minus a is always less than or equal to the integral from a to b of f of x dx is always less than or equal to capital M times b minus a, where little m is the absolute min of f on AB, and capital M is the absolute max of f on AB. So I could give you a function f of x and an interval AB and ask you what's the smallest the integral from a to b of f of x could actually be. And you would go to compute the blue area, which would mean, you would go to compute the purple area, which would mean you'd need to find the absolute min of that function on that interval and then multiply by the width of the interval, b minus a. I could ask you what's the biggest that integral could possibly be, and that would mean you'd want to find the red area, which would mean you need to compute the absolute max of that function on that interval and then multiply by the width of the rectangle, which again is b minus a. Do we feel like we understand this now? No, Kitty. No, baby. Don't do that shit. All right. Let's try an example. Your textbook has one here. We'll do theirs. So they want you to use this property. Oh yeah, sure. And I'll show you a more general rule here. So this is one of your rules, right? This is a theorem. Another theorem says if f of x is less than or equal to g of x on the interval a, b, then the integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. Both of these theorems are sort of comparison properties for an integral. And you can think of the first theorem as being a consequence of the second theorem, but it takes a little bit of work to get from one to the other, so you might as well think of them as separate things. So let's solve a problem. Yeah, why not? Sorry, I'll leave this for just a second longer in case anybody is still writing or drawing. I want you to get good notes. Okay. So I could ask, what is the largest and smallest possible value of the integral 0 to 1 e to the negative x squared dx. So to do this, we need to find the absolute min and absolute max of the function f of x equals e to the negative x squared on the closed interval 0 to 1. And because this is a continuous function and this is a closed interval, there is guaranteed to be an absolute min and an absolute max. To find those, we first take the derivative. The derivative of e to the negative x squared. Anytime you differentiate e to some stuff, you get e to that stuff back. But then you need to multiply by the derivative of the inside. The derivative of negative x squared is negative 2x. So this is negative 2x times e to the negative x squared, which satisfies, or let's say which has critical numbers where f primed of x is 0 or f primed of x is undefined. This never happens. This happens at x equals 0. Why is it never undefined? Because this function is continuous everywhere. It's a composition of an exponential and a polynomial function. And the thing it's being multiplied by is a polynomial function, which is continuous everywhere, so it's never undefined. But it is equal to 0 when x is 0. All right, if you plug in 0 here, this is negative 2 times 0 times e to the 0, which is 0 times 1, which is 0. So if you set this equal to 0 and separately set this equal to 0, you get one solution, and it comes from this guy, and that's x equals 0. So you can make a number line for f prime, which will tell you where f is increasing and decreasing. The only thing that really belongs on there is 0, because that's our only critical number. If you test a number to the left of 0, like -1, then f primed of -1 is -2 times -1 is 2 times e to the -1 squared. That's e to the -1, because the negative is outside the square. -1 squared is 1. Negative 1 is -1. This is 2 over e, which is a positive number. So f primed is positive to the left of 0. And if you test x equals +1, on the right, f primed of 1 is -2 times e to the -1, which is negative. So you have a max at 0. We don't yet know whether that is an absolute max or just a local max. But it's definitely a max. To determine the absolute min and absolute max from here, we need to compare the value of the function at 0, the original function, which is e to the -x squared, so that's e to the -0 squared, which is e to the -0, which is e to the 0, which is 1, with the value of the function at the endpoints. Yes, it's never undefined. Yeah, sorry, this is never. No, you're good, you're good. So 0 happens to be one of the endpoints of my interval. So I don't need to check both of the endpoints separate from this. The only other thing I need to check is f of 1, which is e to the negative of 1 squared. 1 squared is 1, so that's e to the -1, or 1 over e. And there's nothing else to check. So the absolute max is 1, and that's attained at x equals 0, and the absolute min is 1 over e, and that's attained at x equals 1. In other words, little m is 1 over e, and big M is 1. Therefore, little m times b minus a is 1 over e times, well, what are a and b here? Remember, we're integrating from 0 to 1. So this is 1 minus 0. This is just 1 over e. And big M times b minus a is 1 times 1 minus 0 is 1. So the smallest my integral could be is 1 over e. And the largest my integral could possibly be is 1. And that's the job done. In other words, this business of finding absolute mins and absolute maxes comes back in this setting when we want to approximate integrals. A fun fact, even with the tricks I'm going to show you on Wednesday, this integral right here, the e to the negative x squared integral, regardless of where these bounds are, unless it's like 0 to 0 or 1 to 1, is a very hard integral to solve. And when I say very hard, I mean not only am I not going to teach you how to do it in this class, but there's no finite number of steps you can do to solve this integral. It requires infinitely many steps. It requires some stuff that you'll learn at the end of Calc 1, and then the answer is not a nice looking answer. It's an infinite series. But we can approximate it here. You could get a better approximation than, is somewhere between 1 over e and 1 by using Riemann sums. But through this relatively easy method, we're able to say that this integral is definitely bigger than 1 over e and definitely smaller than 1, which is not bad. All right, how are we doing on time? I think we're probably, about out of time. We can look at 1 or 2 more examples. So here's the picture that goes along with that. They've graphed e to the negative x squared from 0 to 1. Here's the little rectangle. And here's the big rectangle. And here's the result. So just for shits and giggles, let's look at 1 or 2 more of these. Yeah, we can find Riemann sums all day. We've done plenty of that. Here's the midpoint rule. Prove this. And calculator, express the limit as a definite interval. Let's do one of these. I've given you guys a little bit of this in the past. Or maybe what would be more fun? By interpreting those areas. All right, let's make life challenging. Let's look at number 37. I've got you guys for just a few more minutes. Let's take a look at this guy. I'll write it down and then we'll switch back to the document. Because here we require you to remember a little bit from pre-calculus that we haven't talked about in a minute. The first thing I would do, looking at this problem, is split it up. So the integral from -3 to 0 of 1 plus the square root of 9 minus x squared dx is the integral from -3 to 0 of 1 dx plus the integral from -3 to 0 of the square root of 9 minus x squared dx. So I need to find the area under this guy from -3 to 0 and the area under this guy from -3 to 0. So I'm going to look at 2 graphs. I'm going to look at the graph y equals 1, and I'm going to look at the graph y equals square root 9 minus x squared. The y equals 1 graph is not challenging. That is a constant function. And if -3 is out here, then here's that area. Oops, sorry. Here's that area. So the integral from -3 to 0 of 1 dx is this width times this height. That's 0 minus -3 times 1, which is 3. Right, it's the integral of a constant function. So it's b minus a times the constant. This guy, on the other hand, does anybody know what this graph looks like?
Parabola?
It's not a parabola. It is a curvy thing, but it's not a parabola. If you square both sides, then you'll get y squared equals 9 minus x squared. And then if you add x squared to both sides, you get x squared plus y squared equals 9. Does anybody recognize it now?
Circle?
Good, it's a circle. Where's the center? What's the radius?
The radius 3?
Good.
The radius 3 and the center is at 0, 0.
Perfect. So if you guys don't remember what equations of circles look like, now's a good time to jog your memory. This is not only going to be important in this section, but it's also something that we do a lot with in Calc 2 when we get to section 7.3 of the textbook. So if I want to draw this graph, that is a circle centered at 0, 0 of radius 3. But since the thing they gave me was just the positive square root, it's really just the upper semicircle. There is, in the form that I wrote it with x squareds and y squareds, you get the whole circle. But here, to get the whole circle, you would need a plus and a minus. So this piece, this is the upper semicircle. Which means the integral from -3 to 0 of the square root of 9 minus x squared dx, that's this area. So that's 1/4 of the area of a circle of radius 3, which is 1/4 of pi times 3 squared. In other words, this is 9 pi over 4. So altogether, the integral from -3 to 0 of 1 plus the square root of 9 minus x squared is integral -3 to 0 of 1 dx plus integral -3 to 0 of the square root of 9 minus x squared dx is 3 plus 9 pi over 4. And that is job done. So this is what I'll be giving you guys to work with for the most part this week. At least between now and Wednesday, this is what I want you guys working on. I will be giving you other stuff too. Wednesday, we're going to talk about the fundamental theorem of calculus, which I kind of teased last Friday. Connection between differentiation and areas, or differentiation and integration. But now that you know exactly what the definite integral is, and you're familiar with some of the properties of the definite integral, you'll be able to make better sense of the things that I kind of teased last Friday. So between now and Wednesday, I would love it if you guys would work on the first few problems of the homework set that I'm going to open up today. It'll be open in just a few minutes after class. I got to go through and make sure everything is as I want it, and then I'll publish it. And then when you get to the problems that ask you to use the fundamental theorem of calculus to evaluate the integral, you can stop. And we'll talk about those on Wednesday, and you can work on them from Wednesday on. That is all I have for you guys. Are there any questions for me before we call it a day?
Is exam 3 gonna be before or after Thanksgiving break?
After.
Okay.
Yeah, exam 3 will be our last day of class. Any other questions?
Do you have an exact date or is it,
December 4th.
so it's gonna be exactly on December 4th?
Yeah, December 4th is our last day of class. So yes, December 4th during class time, that's exam 3. And then your final exam is December 7th. And it's at a weird time. It's from 1 to 3. So I would put all of those things in your notebook. And if we do finish these other topics for exam 3 before the last day of class, then I would be happy to leave a little bit of extra time here to review for the final. But usually, you know, like we've fallen about a week behind as we took time on different things. So this last week will probably be us just wrapping up the areas between curves and U-sub stuff. So yeah, I would count on exam 3 being December 4th. And then your final exam is definitely December 7th from 1 to 3 p.m.
Is
It
the
would be
final
wise
going to be
to
online or on
use your
campus?
calendar. I'm sorry, what was that?
Is the final going to be online or on campus?
It'll be the same as all of our other tests. So it'll be online in Canvas using HonorLock, unless some miracle happens and they give me permission to do things in person, but I'm not expecting that. All right, any other questions?
If we're going to be outside of the country by the time of the final, do you know if HonorLock has any problem with?
I have no idea. Honestly,
Is
I
there
really
an
don't.
HonorLock like customer support that I can ask?
Yes, there is, and you certainly should do that. Yep.
Okay,
Go
I'm
to
gonna do it right
HonorLock's
now.
website. You can start a chat with them, or you can call them. They have a phone number there too. Definitely make sure you figure that out before leaving. Otherwise, we'll need to come up with some alternatives.
Of course. Thank you.
Alrighty, gang. I'm gonna go ahead and sign out. I will see you guys next time. I hope you have a lovely rest of your day. Please work hard on this homework set, and Wednesday we'll get to the fundamental theorem of calculus. Take care, y'all.